Okay, so we got quite a bit of stuff going on. Mainly, the main thing we've got going on is we're just out of time in this semester. So we're going to be zipping through material. We've got tonight. We will not meet next Wednesday because of Thanksgiving. And then we've got the week following Thanksgiving to meet. Then the week after that is the final exam. So we've got 2 more class meetings. Then our 3rd class meeting will be the final exam. So obviously we've got a ton of stuff to get through. And so we're going to be kind of surveying the important stuff. That's what we're going to be doing. I am currently posting videos from my Monday night class, which is the 401 class, sort of the intermediate algebra class. And what we've done in that class, what we're doing the last couple of weeks there, is strictly going over stuff that we're going over in this class. So because we did a lot of stuff in there Monday, that's kind of the same, a lot of the same stuff we're going to be going through tonight, I'm going ahead and posting those videos in our college algebra lecture video folder in the 13-14 class. So if you're not in the 401 class, you could still watch that video if you wanted to. We're going to be going over a lot of the same stuff tonight, but I've tried to use different examples, so that'll give you more examples to look at if you need to go back through those. And I'll get these videos posted also as soon as I can. So I've got y'all's tests. I'm not going to stop class to hand them out. That's what you get for being 2 minutes late. But at break, remind me at break, and I'll give you your test back. Ashley, did you get your test back there in Sulphur Springs? Drum roll. Ashley, did they give you back your test in Sulphur Springs?
They did.
Okay. Stephanie, it looks like you got yours, yeah?
Yes.
Okay, good deal. All right, Greenville, if y'all came in late, I'll give it to you straight, but we got to get rolling here. So I know that we still got 2.7 and 2.8 out there. That's those last 2 questions from the test that I told y'all to omit. We're going to cover exactly what we need from those sections just to be able to answer things that are on the final exam from over that. And you don't have to do those 2 sections of homework. So 2.7 and 2.8. If you do those and you make a 100 on them or whatever on those homework assignments, it would help your grade. I would count them. But otherwise, I'll just omit sections 2.7 and 2.8 at the end of the semester. So the only stuff you're responsible for in chapter 2 homework-wise is 2.1 through 2.6. The other thing I've decided, and I haven't announced this yet, but I'll tell y'all now, is I have decided also at the end of the semester, I'm going to waive the late penalty for homework. So if you're behind on homework, catch up. I'm going to waive the late penalty. And if you do a section that's already past due and get a 100 on it, you'll receive a 100 for it because I'm going to do away with the late penalty when I calculate the grades. So just trying to help y'all see some things you can do to help yourself out. So remember, tonight we're going to cover as much material as we possibly can. And again, we're going to have to move quick. So I'll post the recordings where you can go back through it if you need to. We'll have Thanksgiving next week. The following week after Thanksgiving, we will lecture first half of class. We'll have to, because we'll still have some things we need to get through. In the second half of class, we will have to work through the final exam review. And we'll have to really hurry to get through it because there's 33 problems on the final exam. Let me tell you a couple of things about that final exam. The final exam is 33 multiple choice questions. You will be allowed to use 1 full page of notes front and back for the final exam. You obviously will want to bring your calculator. You're going to find out that week after Thanksgiving that there are a few things that are going to be on that exam that you literally can't do without a calculator. Probably at least maybe 3 problems or so that are undoable without a calculator. the final exam review, which is available now. If you want to print it out and look at it early, it's in your student links now on our course page. I believe the link to the final exam review is just below your grade book in student links. The problem is that final exam review has, I can't remember, like 70 problems on it. Only 33 of those have any bearing on our final exam. And I will actually tell y'all which problems you need to circle on that review. So you might want to hear from me on that. I promised Chelsea I'll try to let her know those because she wanted to kind of look at it early. And what I might do is when I just don't have it with me to tell y'all now, when I get that list of problems that are on the review that actually are germane to the test, maybe I'll just email that to all of you. So if you want to print the final exam review out early and start looking at it, you would be able to know which problems to look at. The other thing that is on our course page, in fact, I can probably fix it right now if y'all just bear with me a minute. Let me find this. Whoa. Somewhere. No. I know y'all are like, what's he doing? But I'm doing something. Y'all just trust me on this. Where is it? There it is. Okay. All right. So the final exam review, I've made it available. Again, it's just below your grade book in your student links. I have now made available the video of the final exam review. So if you did want to start looking at it early, we're not going to meet for 2 weeks after tonight. If you did want to start looking at it early, you could go through that final exam review and you'll see exactly the video. You could go through that final exam review video and you'll see exactly which problems on the review matter. But I will get hard copies of the review to y'all in class next time, which will be the week after Thanksgiving. Don't forget, though, that also you're going to get that take-home assignment that we're counting as test 3. And obviously, you're going to have to get on that first and get that knocked out because, you've got a week to do it. You've got to hand it in when you come in to take the final. Obviously, there's no more other time to grade it. But, when you get that thing, you'll want to jump right in on that and get through it, because you will need to save a little time probably to go through that final exam review. But we will work through it in class as well. So that's where we are. Let me get back to real life here. And we're going to get started because, again, we've just got way too much to do. In fact, I am recording, just so y'all know. You may have to remind me when it's break time because I might get rolling. So we're going to be taking a look at Chapter 3. Tonight, and we're going to get as much of it done as we can. The first section of Chapter 3 looks specifically at quadratic functions. For those of you who are in the Monday class, you've already seen some of this, but I tried to make sure the examples we're using tonight are different examples. And again, I'll be posting the video from the Monday night class and the video from this class in the lecture videos folder in the college algebra course. Okay, so 3.1 quadratic functions. So the first question is what is a quadratic function? This is kind of the general form, and I know this is math gobbledygook I'm going to be giving you on this first page, but just take a look at it, write it down, whatever. We're going to work through some examples so you can see what's going on. The important thing to see here is that a quadratic function, it could say y equal or it could say f of x equal. It's the same thing. A quadratic function is one where you have an x to the second power term. So remember in 2.3, we looked at those linear functions that looked like y equals mx plus b, where you only have x to the first power, and those are called linear functions. And the reason, of course, is because we saw that when you graph one of these, the graph is a line. Quadratic functions, involve a quadratic expression. In other words, your highest degree variable term is x to the second power. And when you graph this kind of function, the graph is always a parabola. P-A-R-A-B-O-L-A, parabola. And it's always either a parabola that opens, sorry, I know this is small, but I don't have much room to write. It either opens up like this, or it opens down like this. So that kind of U-shaped. We used a parabola when we were looking at y-axis symmetry in chapter 2. That graph we saw that had y-axis symmetry was a parabola. So every quadratic function's graph is a parabola. So really what we're trying to figure out in this section, think of it this way: we want to figure out how to come up with exactly the information we need about whatever quadratic function we're looking at. We want to be able to find all the information we need to be able to draw a reasonably accurate sketch of its graph. Let's just think of it like that. So here's the stuff we need to know. We need to know, does that parabola open upward? Y'all look, like this one, where it's going up on both ends, or does it open downward like this one? It turns out there's an easy way to figure that out. And this says that it opens up if a is greater than 0. Notice a is the coefficient of the x squared term. And it opens down if a is less than 0. Just think of it like this. If the squared term is positive, it's going to be one of these parabolas that opens up. And if the squared term is negative, it's going to be one of these that opens down. Everybody with me there? Super easy. You just look at the highest degree term, that second degree term. Up if the second degree term is positive, it opens down if it's negative. We want to be able to find the vertex. The vertex, y'all look, is this point. Or if it's one that opens down, it's this point. It's that highest point on the graph if it opens up, or the lowest point on the graph if it opens, the highest point on the graph if it's a parabola that opens down. It's the lowest point on the graph if it's one of those parabolas that opens up. And we want to be able to find exactly what ordered pair represents the vertex, and here's how you do it. This little subscript of v here, where this says x subscript v, usually you would say x sub v, that simply means the x coordinate of the vertex. That's just my shorthand to say the x coordinate of the vertex is negative b over 2 times a. So notice b is the coefficient of that x term. A is the coefficient of the x squared term. So whatever that coefficient of the first degree x term is, you put the negative of that over 2 times whatever the coefficient of the x squared term is. Everybody with me there? It's super easy. Just negative b over 2a. That's the x coordinate of the vertex. To find the y coordinate of the vertex, of course, you just plug the x coordinate into the function. And that's why it says the y coordinate of the vertex is just f of the x coordinate of the vertex. Whatever the x coordinate of the vertex turns out to be when you calculate negative b over 2a, you plug that number into the function, and whatever you get, that's going to tell you the y coordinate. Everybody with me? So the vertex is an ordered pair with an x coordinate and a y coordinate. And of course, you could plot that point. That's the vertex of the parabola. You want to be able to figure out where it hits the y-axis. That's easy. Whatever the constant term is, that's the y-intercept. Just like how when we looked at y equals mx plus b, remember b was the constant term and that was our y-intercept. It turns out that with any polynomial function, whether it's first degree or second degree or 30th degree, the constant term is always the y-intercept. So super easy. Just look at it. See the constant term, you know where it hits the y-axis. The x-intercepts is where we actually have to do some work. So for these x-intercepts, we have to set this function equal to 0. In other words, we need to write ax squared plus bx plus c equals 0, and then we need to solve that equation. The reason that works is because, remember, all this is equal to y, right? And so when you set this equal to 0, it's kind of like you're saying, okay, y is equal to 0. What are the x values that make y 0? We know that all the points on the x-axis as 0 is the y coordinate. So we know how to solve this kind of equation. We can either factor it and figure out what makes each factor 0, or if it couldn't be factored, or maybe we can't figure out how to factor it, we could use the quadratic formula to solve it, right? So we've got a way to do that. Okay, so let's look at some examples. That's probably the best thing for y'all in terms of figuring out what we're doing here. Oh, great. I drew my arrows and stuff on that and it bled through. Sorry about that. So here's our first example. We want to sketch the graph of the equation y equals x squared minus 4x plus 3. There's a couple of things I can fill in without having to do any math at all. For instance, does everybody agree that when I graph this, the graph is going to be a parabola that opens up? Do y'all see that? Remember, if the x squared term is positive, and that is positive x squared, it opens up. So we know this is one of those parabolas that opens upward. Everybody with me? The other thing we can do without doing any work at all is we can figure out the y-intercept. What is the y-intercept? 3. It's the constant term, right? So it's going to hit the y-axis at 3. Now, the vertex and the x-intercepts, we're going to do a little bit of work there. So for the vertex, to find the x-coordinate of the vertex, we're going to use that little formula, negative b over 2a. And so notice that for our particular problem, y'all look up, if you're looking down, does everybody see that x squared is the same as 1x squared? So our a is 1. Our b is the coefficient of the x term, so our b is negative 4. And of course, we've already used the fact that our c is equal to 3 for the y-intercept. So, okay then, negative b over 2a is going to be the negative of negative 4, which of course is going to be positive 4, but we'll just write it in there. Negative of negative 4 over 2 times a, and our value of a is 1. And of course, the negative of negative 4 is 4. And of course, 2 times 1 is 2. And 4 over 2 is equal to 2. Everybody with me there? Now, that is not the vertex. That's sort of half the vertex. That's the x-coordinate of the vertex. Now we need to find the y-coordinate of the vertex. And all we do to accomplish that is this x-coordinate 2. If we just plug it into this function, then that's going to tell us what y is when x is 2. Everybody see? So the y-coordinate of the vertex is going to be 2 squared minus 4 times 2 plus 3. That's pretty easy to calculate. 2 squared is 4. Negative 4 times 2 is negative 8. And we got plus 3. And 4 minus 8 is negative 4, and negative 4 plus 3 is what? Negative 1, right? So now we can say what the vertex is, and y'all look, this is how you're supposed to say it. It's the ordered pair 2 comma negative 1. That's our vertex. Everybody see that? That's all you do to find the vertex every time. You plug in to this formula, negative b over 2a, you calculate what number that is the x-coordinate of your vertex. Then whatever that x-coordinate of your vertex is, you plug it into the function to find the y-coordinate of your vertex. Everybody with me? And again, the vertex is a point, and of course it's represented as an ordered pair. We got our y-intercept, it's just a constant term. X-intercepts. This is the one where we have to do a little bit of algebra. To find the x-intercepts, you set this function equal to 0. So in other words, I need to write x squared minus 4x plus 3 equals 0, and I need to solve that. Everybody with me? And this is easy because you can factor it. You can see you've got to start with x and x, because x times x is the only way to get x squared. The last two numbers multiply to be positive 3, so they have to have the same sign. Those same numbers add to be negative 4, so they have to be both negatives. And it should be pretty easy to see it's going to be x minus 1 times x minus 3. Everybody see that? See, negative 1 times negative 3 is positive 3. And negative 1 plus negative 3 is our middle number, negative 4, so that's correct. And do y'all see that the two solutions to that equation are 1 and 3? Because remember, whatever makes a factor 0 solves the equation. And 1 minus 1 is 0, so 1 is a solution. And in the second factor, 3 minus 3 is 0, so 3 is a solution. So those are our x-intercepts. There's one more thing down here, the axis of symmetry. We're going to talk about that in a minute when we sketch this graph. So what we want to do now, we've got all the information we need. We know that it's going to be a parabola that opens upward. We know what the vertex point is. We know where it hits the y-axis. We know where it hits the x-axis. So we're going to sketch the graph. So let's see, it opens up. Okay, the vertex is 2, negative 1. So that's the point where I go out to 2 and then I go down 1 unit. Everybody see that that is the point 2, negative 1. 2, negative 1. We know our y-intercept is 3. 2, 3. There's the y-intercept. The x-intercepts, remember, are 1 and 3. It hits the x-axis at 1 and 3. Because we know the graph is a parabola, we can draw a pretty good representation of the graph. But this axis of symmetry thing kind of comes into play. So let's take a look at what happens here when, with the information I've got, y'all look, we've got our vertex, we've got our y-intercept at 3, we've got our x-intercepts at 1 and 3. So here on the left side of the graph, I'm going to call it the left arm of the graph, I've got 3 points to sort of guide my pen. I've got the vertex, an x-intercept, and a y-intercept. And I can just kind of draw the left arm of the graph. Now notice on the right arm of the graph, I don't have 3 points. I only have the vertex and an x-intercept. So there is something we can do to make our graph a little more accurate, and it does not require us to do any more calculation or arithmetic or algebra. Parabolas are symmetric. And if I was to draw the vertical line that goes through the vertex, everybody with me? This vertical line that goes through the vertex, this graph is a mirror image of itself on either side of that vertical line. Everybody with me? Remember when we did the y-axis symmetry, when we talked about y-axis symmetry, we used basically this graph. We said that has y-axis symmetry because it's a mirror image of itself on either side of the y-axis. Well, see, this vertical line, the y-axis, is the axis of symmetry for that parabola. Here, the y-axis isn't the axis of symmetry. This vertical line that goes through the vertex is. The reason that helps us is, notice how our x-intercepts, this are 1 and 3. Notice how this x-intercept is exactly 1 unit to the left of the axis of symmetry. And this other x-intercept 3 is exactly 1 unit to the right of the axis of symmetry, right? Makes perfect sense because it's a mirror image of itself on either side of that line. Well, here's how you can pick up one more point on the right arm of this graph without having to do any math at all. if you notice this y-intercept, it's at 0. I mean, it's at the point where x is 0 and y is 3. This vertical line has every point on it has 2 for its x coordinate. Does everybody see that this y-intercept is exactly 2 units to the left of the axis of symmetry? Everybody with me there? Then if I go 1, 2 units to the right of the axis of symmetry, that would be where x is 4. Then if I go exactly 2 units to the right of the axis of symmetry, I'm going to see that up here, that must be another point on the graph. See, this was the point where x is 0 and y is 3. If I look 2 units on the other side of the axis of symmetry, I see that's going to be the point where x is 4 and y is 3. And that gives me 3 points on the right arm of the graph. Just makes my graph maybe a little bit more accurate, you know, when we're hand drawing it, right? Because if I couldn't do something like that, of course, it's still not great because my tick marks are closer together here than they are here. But you know, if I didn't have that axis of symmetry, maybe I start drawing this arm of the graph and I wind up with something like that, you know, or something way off. So the axis of symmetry is a vertical line. Remember, every vertical line has an equation that looks like x equals some number. Well, the axis of symmetry goes through the vertex, and the x coordinate of our vertex is 2, right? Why did I write 3 there? The x coordinate of our vertex is 2, then the equation of our axis of symmetry is simply x equal 2. That's the equation of that vertical line. Every point on the line has 2 for its x coordinate. Now, on that take-home assignment that we're counting as test 3, I never ask you to tell me the axis of symmetry. And frankly, if you've got, y'all look, if you've got this y-intercept and your x-intercepts in the vertex, you probably don't need to pick up another point here. You know, you've drawn this arm of the graph, just draw the right arm so that it goes through the vertex and the x-intercept and try to make it look like a mirror image of the other side. I'm fine with that. But in the homework, they will, I think there might be a couple of problems where they ask you to give the equation of the axis of symmetry. And when you see those problems, the equation of the axis of symmetry is always just x equals whatever the x coordinate of the vertex is. Everybody with me there? Okay, let's look at another example. So we want to graph y equals 4x to the second minus 8x plus 5. Okay, is it going to open up or down? Up, I agree, because that's positive 4x to the second. By the way, do y'all see that when it opens up, that means the vertex is going to be the minimum or lowest point on the graph? Do y'all see that? Because it opens up, the vertex is going to be sort of at the bottom of the graph. I mention that because once in a while you'll see a problem where they give you a function like this and they say find its minimum point. Well, that means find its vertex, right? At any rate, let's find the vertex. So the x coordinate of the vertex is negative b over 2a. Okay, our value of b is negative 8. Do y'all see that? Our value of b is negative 8. So negative b is going to be the negative of negative 8 over 2 times a. Our value of a is 4, the coefficient of the squared term. And so the negative of negative 8 is positive 8 over 2 times 4, which is also positive 8. And 8 over 8 is 1, right? So the x coordinate of our vertex is 1. Now we need to find the y coordinate of the vertex. We're just going to plug 1 into this function. So it'll be 4 times 1 squared minus 8 times 1 plus 5. And 4 times 1 squared is 1, and 4 times 1 is 4. Negative 8 times 1 is negative 8. And then don't forget, we got our constant term there, plus 5. And 4 minus 8 is -4. -4 plus 5 is +1. So our vertex is the point whose ordered pair is 1, 1. Do y'all see that? The x-coordinate of the vertex was 1, and the y-coordinate of the vertex is 1. Okay. What's our y-intercept? 5. It's the constant term, right? Now I'm going to show y'all something. I should have done this on the last problem, but I didn't. But I just wanted to mention to y'all that this is kind of a useful, it's like not something you have to do, but it's efficient. It's useful to do it. Before we start trying to find the x-intercepts, I'm going to go ahead, before I start attempting to find the x-intercepts, I'm going to start a little bit looking at this graph. So what we just found out, if we're going to graph this thing, is that the vertex is the point where x is 1 and y is 1, right? So x is 1, y is 1. Also remember that we found out that this parabola opens up, right? Oh, and I could go ahead and say the y-intercept, we know it is 5, right? So here's the question I have for you. Does every parabola, so let's see if I can, does every parabola have x-intercepts? Like what if I have a parabola that looks like this? Is that going to have any x-intercepts? No, it's never going to hit the x-axis, right? Then what do you think if we had the equation that this graph is, parabola is the graph of, what would happen if we set that equation equal to 0 and tried to find the x-intercepts? Well, we would spin our wheels for a while, possibly drive ourselves to madness, you know, wake up in a straitjacket somewhere, maybe, I don't know. The thing is, not every parabola has x-intercepts. And you've already seen that when we find the x-intercepts, that's where we have to actually do some work, right? We have to set that equal to 0 and solve that equation. So my advice is, once you've figured out how the parabola opens up or down, and you figured out what your vertex is, go ahead and plot that vertex, because I should be able to look at this and tell, is it going to have x-intercepts or is it not? I agree, it is not. How can we see that? Because, right, this is the very lowest point on the graph, and the graph only goes up from here, right? Now, if that was our vertex, 1, 1, and it was one of those downward opening parabolas, we would have x-intercepts, right? But you can see that we're not going to have any x-intercepts at all. So before I start wasting my time spinning my wheels looking for x-intercepts, I want to make sure there are some. Oops, that's the wrong one. What did I do with it? Oh, there it is. Which one? No, that's the right one. Yeah, that's the right one. And they're actually, this is gonna be fun. We can just say none. That was quick, right? If we had tried to set this equal to 0 and solve that equation, what would probably happen is we would try to factor this thing, and we wouldn't be able to figure out how to factor it. You might be able to convince yourself that it's impossible to factor it, or you might just be like mildly anxious thinking, well, you probably can factor it and I just can't figure out how to do it. Either way, at some point you're going to go to the quadratic formula and use the quadratic formula. And I'm not going to do that because we just don't have time. We have no more time in our semester. But I will tell you what would happen if you did use the quadratic formula on this. When you use the quadratic formula, you'd get a negative number under that square root. And you would find out that the only numbers that make this thing equal to 0 are non-real numbers. Non-real numbers don't show up in the real coordinate plane where we have the x-axis of real numbers and the y-axis of real numbers. So that's what would happen. You'd waste a lot of time doing the math to figure all that out, only to realize there are no x-intercepts. But we really could have just figured that out without going through all that misery if we just plotted our vertex and thought about how the graph opens. Everybody with me there? Okay, so we get to just say none. By the way, I think on this take-home assignment, you may get a problem where you're asked to graph a quadratic function, and it might be one where there aren't any x-intercepts. If that happens, don't just leave the x-intercept part blank and don't say anything about it, because that'll make me think you don't know how to find them. Just go ahead and tell me there are no x-intercepts. Y'all see what I'm saying? At any rate, we might as well talk about this axis of symmetry, and we're going to see that this is going to be a case where it's particularly useful. The equation of the axis of symmetry is just x equals the x coordinate of the vertex, which is 1, right? And so when we're graphing, so we know it opens up, we know the vertex is 1, 1. We know the y-intercept, what was it, 5, the y-intercept is 5. We know there are no x-intercepts. We know the axis of symmetry is x equal 1 because 1 is the x coordinate of our vertex. Here's where that axis of symmetry is particularly useful in the case where you don't have any x-intercepts, because notice now I actually only have 2 points for the left arm of this graph, but that's enough for me. Well, it would be if I didn't suck. That's enough for me to, you know, get pretty close to drawing what that arm looks like, but I don't have anything to guide my pen on the right arm of this graph, right? Because there's no x-intercept over here anywhere. There aren't any. But if I just sort of lightly sketch in this little axis of symmetry, then I realize that this y-intercept is 1 unit to the left of the axis of symmetry. Then I can just go 1 unit to the right of the axis of symmetry and realize there's going to be another point here, the mirror image point of that y-intercept. And so now I've got a little bit of guidance trying to draw the other side of that graph. Do y'all see? Everybody see that? And that is a good enough graph for, like, on the take-home assignment. If you get one with no x-intercepts, I'm perfectly happy if you just do that. Plot the vertex and your y-intercept. Use the axis of symmetry to help you find 1 point on the other arm of the graph and draw it. Everybody see that? Okay. We're going to look at one more example, then we've got to move on to the next topic. We're going to look at one more quick example because we haven't seen, there's one thing we haven't seen yet. Is this parabola going to open up or down? Down, and we haven't seen an example where it opens down yet, but notice our squared term is negative. It's negative 2x squared. That means that the parabola, the graph, is going to open down. And also, do y'all see that that means the vertex is going to be the maximum or highest point on the graph, right? That opens down. Okay, let's find our vertex. The x coordinate of the vertex is going to be negative b over 2a. Our b is negative 2, so it's going to be the negative of negative 2 over 2 times a. Well, a is also negative 2. Y'all see that? So over 2 times a, that's going to be over 2 times negative 2. The negative of negative 2 is positive 2. 2 times negative 2 is negative 4. And do y'all see that if I simplify this fraction, I get negative 1/2? Everybody see that? Oh, dear God, what are we going to do? The x coordinate of the vertex is a fraction. How can we possibly do this problem? We've got to find the y coordinate of our vertex. And so we're going to have to plug negative 1/2 here in place of x. So it's going to be negative 2 times negative 1/2 squared minus 2 times negative 1/2 plus 12. Okay, I'm going to go through this pretty quickly, and y'all just know you've got calculators. If you need to use a calculator, then use a calculator here. I'm going to run through it pretty quickly. Negative 1/2 squared means negative 1/2 times negative 1/2, which is positive 1/4, right? 1 times 1 is 1, 2 times 2 is 2, 1 over 4. Negative 2 times positive 1/4 is negative 2/4. Negative 2 times positive 1/4 is negative 2/4, which is negative 1/2. Negative 2 times negative 1/2 is positive 1, right? The 2's just cancel, and you're just left with negative 1 times negative 1, which is positive 1, plus 12. Well, I just did this in my head by saying 1 plus 12 is 13, and 13 minus 1/2 is 12.5, right? And 12 and 1/2, not too hard to figure out, is 25 over 2. So look, I know sometimes fractions pop up, but we don't have any more time to learn how to work with fractions. If you can't figure that out, just use your calculator to help you. So now we've got our vertex. The x coordinate's negative 1/2. The y coordinate is 25 over 2, which again, since we're going to have to plot that, it would be good for us to know that that's 12.5, or if you put it in your calculator, it would tell you 12.5. The y-intercept is 12. The axis of symmetry is the vertical line x equal negative 1/2, the vertical line that goes through negative 1/2 on the x-axis. Let's don't look for the x-intercepts until we make sure we're going to have x-intercepts, okay? So we've got, if we're going to graph this thing, so we just figured out it opens down. And we figured out that the vertex is negative 1/2, comma, the y coordinate's 25 over 2. That's 12.5. So look, what I did here is I did the x-axis by 1, 2, 3, 4, and so on. I did the y-axis by 2, 4, 6, 8, 10, 12, 14, and so on. And so negative 1/2 would be, y'all look, maybe about there, halfway between 0 and negative 1. 25 over 2 is 12.5. Well, here's 12. Y'all can see the tick mark there for 12. So just a little bit above that maybe is like 12.5. And so our vertex is maybe right about there. I'm just guesstimating, where that's negative 1. Negative 2, and that's negative 12. So maybe this is where x is negative 1/2 and y is 12.5, or 25 over 2. Everybody see? Okay, is this thing going to have x-intercepts, yes or no? You're saying yes? Dang it, I was hoping it was no, but it is yes. Do y'all see that? Why? Because this is one of those parabolas that opens down, and you can see it is going to cross the x-axis, right? So, well, oh, and the y-intercept is 12, and of course, that's really close to the vertex. That's because the vertex is 12.5, right? The y-coordinate of the vertex is 12.5. Okay, let's go back and find our x-intercepts. I was hoping we wouldn't have to, but we've got to set this thing negative 2x squared minus 2x plus 12 equal to 0 and solve it. A few ways to do this. You could try to factor it. You could try to use the quadratic formula. I'm going to factor it, but I'm going to do something else first. And this is one of those things that you might or might not think to do, but it's good for you to think to do it. Like, this is one of the things that a person needs to do to become good at math, is to start seeing these kinds of things. Does everybody see that 2 is a common factor of every single term? And so I could factor out a 2. I could pull it out front. Better yet, do y'all see that if instead of factoring out a 2, if I factored out a negative 2, it would make my other factor start with just positive x squared. Y'all see that? So I'm going to do this. I'm going to factor out a negative 2, and that's going to remember, I'm just distributing backwards here. So I need to multiply negative 2 times positive x squared to get negative 2x squared. I'd have to multiply negative 2 times positive x to get negative 2x, and I'd have to multiply negative 2 times negative 6 to get positive 12. Do y'all see that? The reason I wanted to do that is because if you look at this factor, that's much easier to factor x squared plus x minus 6 than negative 2x squared minus 2x plus 12, right? So I've got this negative 2, but this thing's easy to factor. It's got to start with x and x, because x times x is the only way to get x squared. The last two numbers have to have opposite signs because they multiply to be negative 6. But since they add to be positive 1, it must be plus 3 and minus 2. Do y'all see that? Remember, when the signs are opposites, you're really going to subtract and keep the sign of the bigger number. Well, we're supposed to keep the plus sign, right? And get plus 1. So our x-intercepts, whatever makes these factors 0, well, negative 3 plus 3 is 0, and positive 2 minus 2 is 0. So negative 3 and positive 2 are our x-intercepts. So now we've got everything. We know how it opens. We've got our vertex. We've got our y-intercept. We've actually already plotted those. We know our axis of symmetry, and now we have our x-intercepts, which are negative 3 and positive 2. So negative 3 there and positive 2 here. And so my graph then, remember, I got to hit that y-intercept and this x-intercept on the right arm of the graph. So something like that. And then, again, I don't have to use the axis of symmetry. I could just say, okay, I know I've got to go from the vertex and hit this x-intercept, and I want my graph to try to make it a mirror image on the left side of what it is on the right side. So I could just, kind of try to draw that. Technically, I could get another point here, but of course, it would just be a half a unit, right? Half unit to the right of that thing. So there's my graph. Everybody see what we're doing there? Okay, so this is the idea for how we graph these parabolas, and that's the big thing that's going on in section 3.1. We are now moving on. We're going to take a look at a few things in 3.2. Once we look at these things in 3.2, we're going to go to break. And after we get back from break, we're going to kind of skip over. So section 3.3 and 3.4, section 3.3 covers a particular thing called a little algorithm. It's called synthetic division. And really, that's what 3.3 is about, is teaching you how to do synthetic division. The reason they do that in 3.3 is because in 3.4, we're going to use synthetic division, whatever this mysterious thing is, to do some useful stuff. So when we get back from break, I'm going to show you how to do the stuff in 3.3, but I don't believe I made a homework assignment. I don't think 3.3 is assigned, because I'm going to teach you how to do the synthetic division kind of as we begin to see what we're using it for. So I guess you could say then that when we get back from break, we're going to look at 3.4, or maybe the rest of 3.2 if we don't get it finished, and the beginning of 3.4. So in section 3.2, so in section 2.3, we looked at linear functions. Those are polynomial functions where you only have an x to the first power term. Now we've just looked at section 3.1, which was all about quadratic functions, and those are functions where your highest degree x term is x to the second power. Once they get past 3.1, now we're just going to start looking at polynomial functions in general. In other words, your highest degree x term might be third degree, it might be seventh degree, it might be second degree or first degree, could be 10th degree or 20th degree. So we're just going to look at polynomial functions in general. And so what we want to do over these next couple of sections is develop some tools we can use to graph these functions. Now, developing tools to graph, I mean, there's a lot more going on there than just sketching a graph, because when you analyze high and low points on graphs, that might tell you how to maximize your company's profit or minimize your company's cost, or, there's a lot of stuff going on there. But in terms of how to find that information, we can always think of it from the motivation of, okay, if I can find this, 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 and this piece of information, I can draw a reasonable graph of that function. So, okay, the first thing we know about polynomial functions is, let me see if I can get this where you can see part, but not all. All polynomial functions graphs are smooth and continuous curves. Now, smooth and continuous both have technical math meanings. Like there are technical mathematical definitions of what it means to say that a function is smooth or it is continuous. But intuitively, just kind of in layman's terms, we can say this. A continuous curve is one that you, first of all, that you can draw without ever lifting your pencil. In other words, the graph won't be in two different pieces, okay? And it'll have arrows on both ends because it's continuous. You can draw it without ever lifting your pencil, and it goes forever in both directions. Everybody with me? So that's what we mean when we say a function, a polynomial function is a continuous curve. Smooth is even more complicated to explain, but I'm just going to tell you it won't have any jagged edges or sharp points. In other words, notice how these are just, they just kind of curve, you know, the way a road might curve or something. So all of these pictures are some examples of smooth continuous curves. This is a line, and we know that first degree polynomial functions have graphs that look like this. And that is about as smooth and continuous as you can get, right? Here's a parabola. We know that second degree polynomial functions have graphs that are parabolas. This one happens to open down, some of them open up. But some of these, you know, are just like I just created, I just drew some squiggly shapes, right? And so the thing is, you can draw like a polynomial function's graph might have any numbers of humps and dips and so on. Technically, any particular polynomial function can't have more than a certain number of humps and dips. But I'm just saying, if you want a polynomial function whose graph has 100 humps and dips, we could make up such an equation that would happen. And so all these graphs are kind of very different. So the first trick is we've got to start developing tools so that, you know, to sketch a graph, you sort of have to already know what the graph looks like. For instance, when we were working with those linear equations, linear functions in 2.3, we knew because it was a first degree equation, we knew the graph was a line. Well, that tells us a couple of important things. One, we knew what the shape of the graph was. Two, that also told us that we really only needed to find 2 points on the graph, right? Because if you find 2 different points on the graph, there's only one line you could possibly draw. That's got to be the correct graph. So these curves are all very different, but some of them have things in common. Y'all look. These two, for example, the two at the top left, this one, they look totally different. This one's a line. This is some squiggly W looking thing, or I don't know, something. But there is one thing that's the same. Look at the arrows on both of those graphs. Notice how on both of these graphs, the arrows are going up on the left end and they're going down on the right end. And that's true for both of those curves. Y'all see that? What's happening on the ends of the graph, that is called the end behavior. The end behavior of the graph. And so we could say that the end behavior here is, for either of these graphs, is it rises to the left or it falls to the right. That's how your book says it. Like in the homework problems, if they're talking about end behavior, they'll talk about rising to the left, falling to the right. I usually just say up, down, or up on the left, down on the right. If you look, These two graphs, y'all see the two I'm pointing at here. These two graphs also have the same end behavior. Do y'all see that? It's down, down. And this one is down, down. Falls to the left, falls to the right. Now, between the two ends of those graphs, y'all look, between the two ends of those graphs, those curves look quite different. But on the ends, they look kind of the same. These two kind of look the same, right? It's down on the left end on both of them, up on the right end on both of them. They have the same end behavior. And these two have the same end behavior, right? It's up, up, and this one is also up, up. Everybody? So what we've seen there are four different types of end behavior. If you just look at these four graphs down the left side, we've got, well, we can't just look at those. Let's start here. Let's start here. So this one, these two, we got up, up. I'm just going to say it like this. Up, up. That's these two, right? Or if you look at the two above them, they're down, down. Y'all see that? And y'all see how I'm just sort of drawing a little picture to show what it is. Then we've got, let's look at these two on the lower left. We'll say those are down, up. Down on the left, up on the right. And then these two at the top left are up, down, right? Up on the left, down on the right. And I think if y'all look at that a second, you should be able to convince yourself that those are the only four possible end behaviors, right? That's every possible combination of what the arrows could be doing at the ends of the graph. So as we're trying to figure out how to sketch the graph of these various equations that are polynomials, polynomial functions, one thing we can do is try to figure out what the end behavior for that graph is going to be. Now, again, we're obviously going to need more information than that, because knowing that it goes up on both ends, well, so does this one. That doesn't really tell me anything about what's going on in the middle of the graph between the ends, but it's a starting point. It's a place to start, right? And the reason I like starting here is because it's a super easy place to start. This little table here will tell you every single thing you need to know about end behavior. At least it will once I show you what this table means. So here's what this is saying. When you have a polynomial function and it's written out, you know, as an equation, f of x equals whatever, or y equals blah, 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 you look at, there's two things you look at. You look at the degree of the function. In other words, you find the highest degree variable term and you look at what that power is. You know, is it 5th degree? Is it 7th degree? Is it 6th degree? We've looked in the first part of class at 2nd degree. We looked in section 2.3 at 1st degree. You look at the degree of the highest degree term, and then you look at that highest degree term and determine whether it's positive or negative. You know how with the parabolas, we said if that highest degree term is positive, it opens up on both ends, going up on both ends. And if the highest degree term in a second degree function is negative, it opens down, that kind of thing. Okay, so let's look at what this means, and I think it'll probably be helpful if we just look at some examples as we do this. So let me see if I can get both of these on the screen at once. Okay. So, sorry, my anal retentiveness is getting to me. My OCD is kicking in. I got to get these papers straightened up or I just can't live with myself. Okay. So let's look at our function f of x. And let's see if we can figure out what this table here is telling us. By the way, this table determines end behavior of a graph of a function. Your book calls this table the leading coefficient test, or at least when we apply what this table says. It's called the leading coefficient test. It's really the leading term test. We're looking not just, so look, in this function f of x, the leading coefficient is 3. The leading coefficient is the coefficient, the number part of the highest degree variable term. Really, we're going to look at that entire highest degree term. So I like to call it the leading term test. So here's what you look at. F of x, the highest degree term is this term 3x to the 4th power, right? So it's 4th degree. The degree of f of x is even. It's 4th degree and 4 is an even number. Everybody see what I'm saying? Then we look to see whether that term is positive or negative. Well, that term is positive 3x to the 4th. And so our table tells us if the thing is of even degree, it is 4, 4th degree, and 4 is an even number. And if that highest degree term is positive, it is positive 3x to the 4th, then the end behavior is up, up. It's up on both ends. And by the way, on the take-home assignment, there's a problem just like this where you're given some polynomials and just asked to tell me the end behavior. Perfectly fine if you just draw the arrows next to each one to tell me that. But in the homework, they'll expect you to pick something like rises to the left, rises to the right, or something like that. Okay, let's look at g of x. It is negative 5x to the 6th plus 10x to the 4th plus 13x squared plus 27. The highest degree term is 6th degree. That is an even number, right? Then it's even. But that term is not positive, it's negative. Y'all see that? It's negative 5x to the 6th. So according to our table, if the degree of the function is even, it is, it's 6th degree, 6 is an even number. But if the term is, highest degree term is negative, well, it is, it's negative 5x to the 6th, then this graph is going to be going down on both ends, right? The arrows will go down on both ends. Everybody see that? By the way, that makes perfect sense because remember, we just looked at quadratic functions. Those are 2nd degree functions. 2 is an even number, right? And if that 2nd degree term was positive, isn't it one of those up opening ones where it's going up on both ends? And if that 2nd degree term was negative, wasn't it a parabola that opens down? It was going down on both ends. Makes perfect sense. Let's look at h of x. That is 2x to the 5th power minus 4x to the 3rd plus 11x. So there the highest degree term is odd, 5th degree. But the term itself is positive. It's positive 2x to the 5th. Well, if the degree is odd, 5th degree is odd, the term is positive, it's down on the left and up on the right. Everybody see that? If we look at j of x, negative x to the 3rd plus blah, blah, blah. Well, x to the 3rd power, 3 is odd, but it's negative, right? That highest degree term is negative. Then the graph of that thing is going to be going up on the left and down on the right. Everybody see that? So notice we don't even need to look at any of these other terms to figure out the end behavior. The highest degree term tells you everything you need to know to figure out end behavior. Now, I'm going to real quickly, no, I'm not either. Yeah, I am. No, I'm not. I'll show you a couple of these. I just want to show you that what we predict happens here really does happen. It'll take me a minute to switch over. We don't really have time for this, but I'm going to do it because I think it's kind of useful to do this sometimes. Y'all bear with me. I've got to go to a different screen and then I've got to share it. So hang with me a second. There we go. Let me come back and share this. All right, so I'll show you just a quick, maybe couple of these. Let's look at our h of x, which you may, if you haven't written it down, I'm about to enter it. H of x was 2x to the 5th minus 4x to the 3rd plus 11x. So, oh, what happened to here? There we go. Okay, so this was our function h of x, and remember we predicted that, if you can see where my cursor is, it was fifth degree and it was positive 2x to the fifth. So based on our table, we predicted that that means it's going to be going down on the left and up on the right. I chose this one because there's something else I want y'all to notice. This is an odd function. Do y'all see that? We've only got fifth degree, third degree, and first degree terms. All the terms are of odd degree. It's an odd function. So we actually know another thing about the graph. Not only should it be going down on the left and up on the right, it should also have origin symmetry, right? And sure enough, there it is, down on the left. It's kind of wiggling through here, up on the right, and I think you can see that that's origin symmetry. If you flipped it upside down, you get the same thing back. Okay, let's look at one more of those. Let's look at that very first one, f of x, and it's a long-winded one. 3x to the fourth minus 5x to the third plus 7x squared plus 2x minus 13. Wow, that's a lot. Make sure I typed it in right. 7x squared plus 2x. Okay, so it's fourth degree, and it's positive 3x to the fourth. So our little leading coefficient test table tells us it should be going up on the left and up on the right. It's in behavior, should be up, and sure enough it is. It's kind of a wonky looking, like that's not a parabola. It's kind of like lopsided, right? But it's definitely going up on each end. So, okay, back to our thing here. I'm going to leave Wolfram up on my computer just because we might need that again in the second half of class for a minute. But I'm going to go back to the document camera. It is about 10 after 7. Look, give me about 6 or 7 more minutes. We'll take a break and come back, and we may have to finish up just a little bit of this. But I can get one of these examples done, and then we can look at the other one after break, and then we can move on. Okay, let's say we want to graph this equation. So f of x is 2x to the fourth minus 7x to the third. Let me hide all this from you and just look at this. Or let me just zoom in on that part of it. So do y'all agree that the end behavior there is going to be up on both ends? Right? Fourth power, that's even degree. The term itself is positive 2x to the fourth. Then it's up on both ends, right? Because when I say that, some of y'all are looking at me blankly. So I'll try to remember when we go to break, I'll put that little chart back on the document camera in case some of you need to write it down. It's up on both ends. Our problem is we have no idea what's going on between those two ends. However, maybe I can do it this way, 6, 12, 18, 30. Yeah, we can do it that way. Our problem is we don't know what's going on between the ends of the graph, right? Like, does it have humps and dips, or does it not? And how many does it have? And does it, you know, where does it hit the y-axis? Where does it hit the x-axis, if it does, and so on? First of all, y'all should be able to tell me what the y-intercept is, right? It's a constant term. It's 30. Our problem with this is what we really need to be able to find the x-intercepts, but I don't know how to factor this. And if any of y'all know how to factor this, then I should fully retire and let you take over teaching this class. I do not know how to factor this. And I'm pretty decent at factoring, but I don't know how to factor this. In fact, I suspect nobody really knows how to factor this. Like, we don't have some factoring method to figure out how to factor a fourth degree polynomial that has 5 terms. Y'all with me? And we can't use the quadratic formula because that only works if the highest degree term is second power. So I don't know how to figure out where this thing crosses the x-axis, because it is true, we know that if I could just set this whole thing equal to 0 and find all the solutions to that equation, that would tell me all the places it hits the x-axis. Y'all with me? What if I could factor it, though? Just pretend that I can factor it. And let's say that I get it factored, and there it is. So it factors as 2x plus 1 times x plus 3 times x minus 2 times x minus 5. Okay. Now, I don't know how to factor it, but hypothetically, if I could get from here to here, then I could figure out the x-intercepts, right? In fact, if I'm able to get it factored, it's easy. It's going to be -1/2, -3, 2, and 5. Do y'all see that? I use the shortcut here. Remember, reverse the sign. Instead of +1, make it -1, put it over 2, -1/2. -3 plus 3 is 0, so -3. 2 minus 2 is 0, so +2. +5 minus 5 is 0, so +5. These four numbers are called the zeros. So here's a new little term, are the zeros of that function. That simply means these are the values of x that will make y equal to 0. But of course, we also know that the values of x that make y equal 0, those are called zeros of the function. Those are also the x-intercepts of the graph of the function, right? So these are our x-intercepts for our graph. These two terms are kind of interchangeable. So sometimes they might ask you to find the zeros of this function. That's telling you set it equal to 0 and solve it. Sometimes they might say find all the x-intercepts for the graph of this function. Same thing, set it equal to 0 and solve it. The only thing that's different between zeros and x-intercepts, we sort of touched on it a little bit earlier, is you could have zeros of a function that turn out not to be x-intercepts, because what if a couple of the numbers that make your function equal to 0 are non-real numbers? Like what if it turns out that 2 plus I and 2 minus I will make the function 0? Well, those are zeros of the function. If they ask you to find all the zeros, they'll expect you to find those too. But those wouldn't be x-intercepts, because only the zeros that are real numbers are x-intercepts showing up on the graph. But these are all real numbers, so let's see if we can graph this thing. So here's what we know. Let me zoom back up a little bit. So we've already determined that the end behavior is up on both ends. Our y-intercept is 30. By the way, I'm trying to go here by 6, 12, 18, 24, 30, because I didn't have room to get it on there. So our y-intercept is 30. We know it's up on both ends, and our x-intercepts are -1/2. So y'all look, there's -1. So I'm just going to go about halfway between -1 and 0 and say that's -1/2. -3, that's here. +2, that's here. And +5, 3, 4, 5, that's here. So there are x-intercepts. There's our y-intercept. We know that the graph is going up on both ends, right? We know that the graph has to hit every one of these x-intercepts. We also know it can't cross the x-axis anywhere else except at those x-intercepts, right? And we know we've got to hit this y-intercept. Well, it turns out that all I have to do now is play connect the dots. I'm going to hit this x-intercept, which remember is -3. I'm going to pass through the x-axis, but I have to turn in time to come up and hit that x-intercept, -1/2, right? We have to hit that point, and I'm going to come through the x-axis and up and hit that y-intercept, 30. And I don't know exactly where I turn, but I know I have to turn in time to come down and hit that next x-intercept, which is +2. And let's say I pass through the graph, the x-axis, okay, but I've got to turn in time to come hit this other x-intercept. Y'all see that? So I've got to turn somewhere, hit that one, and then if I go through, I finish going up, just like I'm supposed to do, and that could be the graph of the function. When I say it could be the graph, it's not perfect. First of all, because I drew it freehand. Second of all, because algebra will never let you figure this out. You know how we were able to find the exact ordered pair that represents the vertex point of the parabola? In general, like this point and this point, those are relative minimum points, right? And then this point here, this relative maximum point, algebra is not enough to find those exact points. You need calculus for that. So that's something you'd have to learn in a later course. So we don't know exactly where it turns. Like maybe this is real steep and maybe it goes way down before it turns and comes back up, right? We don't really know that, or that. But we still have a pretty good general sketch of the graph. And when we come back from break, maybe we'll take a look at the graph the way the computer draws it, just to see whether what we did looks like the correct graph. Okay, we're going to take a break. I'm going to put that little chart back up because I kind of feel like some of y'all didn't write it down, and I'm thinking if you might need to write it down, because you really do need to just get to the point where you can just look at a function and immediately know its end behavior. All right, I'm going to stop the recording, and I'll help me remember to start it back.